I'm going to go over 310, which is linear approximation and differentials. I'm going to go over this quickly. We just want you to have an introduction to this topic, and that's all you really need. So we'll go over it kind of quickly, and I'm making it pretty easy for you. So first of all, we need to talk about what a linear approximation is. It turns out all it is a tangent line at a particular x equals a value. So we know all about tangent lines already. We're just sort of giving it a new name and calling it a linear approximation. So a tangent line, of course, is a straight line, and it's shown here in blue. Now we're just calling this the linearization at x equals a, instead of the tangent line at x equals a. So the reason we're calling it the linearization is we're talking about it in the context of approximating a function f of x near x equals a. So this is done a lot in practice in computing, physics, where having a function that's kind of complicated, or maybe you don't know the equation of that line. Just notice this was not lined up. Let's make this line up. Then you really increase your speed if you use the linearization. And maybe the value doesn't have to be perfect. It just needs to be close enough within some allowable error. And you really care more about being able to compute it quickly. So it's used a lot. Your book has this linearization equation, which I don't care if you use it all, but I do want to at least speak to it a little bit because that's what's in your book. It says L of x is equal to f of a plus f prime of a times the quantity x minus a. So it looks like something kind of foreign, but in reality, if you just look at the point slope form of a line, y minus y1 equals m times the quantity x minus x1, then we're just doing a few things here. We're plugging in for y of 1, not y of 1, y sub 1, f of a, and the slope is f prime of a, and then our x1 is a. So if you do that, add f of a to both sides, that's exactly the equation that's given for linearization. But in reality, you can just find that what I would do, and what I'll show you to do shortly, is that if you're asked to find the linearization of a function at x equals a, then just translate that what they're asking for is the tangent line equation, and then you already know how to do that problem. So you don't have to memorize this special form. Alright, so I already kind of mentioned some of this stuff, just kind of doing presenting an example, and then we'll kind of backtrack and actually derive it, I guess. In physics, y equals sine of x is often approximated with just y equals x. So I'll go over how you find that. But just to kind of show you what's going on here graphically, what this means, when you're in the neighborhood of x equals 0, which is right in the middle here at the origin, then notice how the line y equals x, or the linearization at x equals 0 of y equals sine of x, is a really darn good approximation. And then once you move out of that range, of some range, then it starts not being a good approximation on this blue line for what y is when you're actually trying to tell what the y coordinate on the black line is. So, you know, it's only working good around the neighborhood of x equals 0. So, to kind of show you where that comes from, you just find the equation of the tangent line of y equals sine x at x equals 0. That's it. And if you want to call it y equals L of x, then, you know, that's icing on the cake. But even if you leave it, the L of x as y, that's fine with me. So finding the equation of the tangent line to y equals sine x involves finding the slope. So to do that, we're going to take the derivative of y, and we of course get cosine. And then we're going to go ahead and plug in x equals 0, cosine of 0 is 1. So our slope is 1. So then the next thing is use your favorite form of the equation of line, and you have the slope, you have the x coordinate, where a is 0. Actually, we need to find the y. That's just plugging in 0 in the function for sine, um, the function sine x, so we get sine of 0, which is 0. We have all the things we need, so if we do this y equals mx plus b style, what this implies is that we have 0 is equal to 1x plus b, forgot my x, and I did my y wrong, so let's really backtrack here. Oh no, that's right, they're both right, sorry, too many zeros. 0 is equal to 1 times 0 plus b is just 1 times 0, 0, so our b is 0. So overall we have y is equal to 1x, or x, plus 0, or just y equals x. So that's how we go ahead and find the linearization of sine x at x equals 0. So basically you need to remember, like in this problem, find the linearization of f of x is equal to the square root of x plus 1 at a equals 3, that all that is find the equation of the tangent line at x equals 3. That's all it's asking for, and you know how to do that. So what we do for the slope is we find the derivative. This one involves the chain rule. This function, we should prep it by writing it as x plus 1 in parentheses, the 1/2 power. So now we can see that the outside function in the chain rule is the power 1/2. So the derivative of the outside function evaluated the inside function is 1/2 parentheses x plus 1 to the negative 1/2 power. Then, with the chain rule, we take the derivative of the inside function, x plus 1, which ends up just being 1 in this case, but sometimes it can be different, so we have to make sure we're doing that extra step in general. So, now what we need to do is we're finding the slope specifically at x equals 3. So we got to plug in that 3 and figure out what we get for a value. So what we get here is 1/4. So last thing, before we start working on our equation of the tangent line, we have the slope, we have the x value 3, is we need to find the y value. And so all we need to do is plug in 3 for x in the original function. So the y coordinate is 2. Spice things up a bit, I'm going to use the point slope form just to kind of model that other version of figuring out the equation of the tangent line. So I'm going to have y minus 2 equals 1/4 parentheses x minus 3. Let's write that in y equals mx plus b form. So plus 2/4, so I'm going to do some fraction action here. Need a denominator of 4, so plus 8/4. So overall we're looking at y is equal to 1/4 x plus 5/4. So if you stop there, that's fine. Or if you take this extra step and let y equals L of x, that's kind of the style of the book. So that's it for linearization. Basically remember that the linearization at a particular a value is the next value, and it's just the equation of the tangent line at that a value. That's it. Alright, moving on. Differentials. This is related to linearization, but it is only the estimated change in y, if we wanted to get at that. And there's some applications, especially in economics, that they do this all the time. So anyway, if we want to get at the change in y, but again that's kind of difficult to do, a good way to do this, if you know the derivative, and that's easy to find, then you can just estimate it as the derivative times change in x. So the way that you can kind of think of this coming from, or why that would make sense, if you look at this picture here, we have our curve in black, y equals f of x, and we have our linearization. So this is where the relationship with linearization comes in. And so if we look at this, and I just picked a point on the tangent line here, that's arbitrary r, and the point at which we have the linearization at, then what this is doing is our delta x and dx are the same. The dx and the dy are kind of having to do with the derivative in Leibniz notation. Delta y is our actual change in y with the function that's in black, or y equals f of x. So we want to estimate that, and we know the derivative at x equals a, at p. Then we can get at that approximate change in y with dy, which is kind of way off in this example, just so I can actually put the dimensions on here, by taking the derivative of the function and multiplying it by the change in x. A little handy thing for, instead of memorizing that, it's like writing Leibniz notation, dy over dx is equal to f prime of x in Newton notation, and then just multiplying both sides by dx, which so far we haven't broken up that Leibniz notation, but this is a little thing you can do, and the notation comes from this, that dy, this approximate change in y based on the tangent line, is f prime of x dx. So the delta x and the dx are the same. The real change in y is denoted as delta y, and the approximate change in y dy is the differential, and that will be different than delta y. So best to do an example to kind of see, put this into action. Consider f of x equals x squared. Find the differential dy when x equals 1 and dx equals 0.01. So somehow you need to remember what the differential is. What I would suggest is just to use your super Leibniz notation skills, dy over dx, write it equal to Newton. They're on equal footing here, co-inventors of calculus. And then here's where things get weird. You multiply both sides by dx. So dy is equal to f prime of x dx. That's what the differential dy is. So now you pretty much have your map on what to do. Dx is given as 0.01, so don't get too worried about that. And then of course you know what the derivative is. And because we're doing this at x equals 1, eventually you're going to plug in x equals 1. So you need to find f prime of 1. So this is actually really easy if you remember what to do and what the differential of dy is. So the derivative here is also very easy, 2x. And then f prime of 1 is very easy, 2 times 1. So finally, just put this together with our dy is 2 times 0.01. So dy at x equals 1 with a dx of 0.01 is simply 0.02. And that's it. So that's actually all the notes for 310. I can stop the recording and then I'll do the notes for 311.